Another test that we can use to show that a series converges is called the integral test. The definition here is we're going to let f be a function. It's going to be continuous and positive and decreasing on the interval from 1 to infinity. If you make a function out of the series terms, the integral and the function of the sum and the sum of the series behave the same way. So basically you're going to start with a series. It's going to have these terms a sub k. What you want to do is look at the function that's equal to the terms of the series. Then we know that the sum and the integral from 1 to infinity of f of k dx, these behave the same way. So if the integral diverges, then the sum or the series diverges. If the integral converges, then so does the series. So do a couple of these. Let's first look at the sum from k equals 1 to infinity of 3 over k squared. And the question is, does this converge, does it diverge? Well, I know that the terms of this series, they do go to 0, so I can't just say that it diverges automatically. So let's try to use the integral test. So the integral test, you just turn that k into an x, and then integrate. So this is an improper integral. I'm going to say this is the limit as t approaches infinity of 1 to t, 3 over x squared dx. So I've replaced that infinity with a t. Then I'm going to actually integrate. So the limit as t approaches infinity. The antiderivative of 3 over x squared is negative 3 over x. And we're going to evaluate this from 1 to t. Then I'll plug in my top and bottom bounds. So that looks like negative 3 over t, and then minus 3 over 1, so that's going to make it a plus 3. Now we're going to evaluate this limit. So the limit as t approaches infinity of negative 3 over t. That means that the denominator is getting bigger and bigger. So this goes to 0, which means my integral went to 3. Because this integral converged, that means that my series also converges. It doesn't converge to 3. That was the integral. This is going to converge to something less than 3, but I do know that it does converge because the integral converged. Next, let's look at the series from k equals 1 to infinity of 2k over k squared plus 1. So let's use the integral test to figure out, does this series converge? Does this series diverge? So I'm going to take my integral. Everywhere you see a k, I'm going to replace it with an x. And we're going to evaluate this. So I'm going to rewrite this in terms of a limit, because you're not really allowed to have infinity as a bounds. So the limit as t approaches infinity of the integral from 1 to t, 2x over x squared plus 1 dx. And then we would use u substitution to solve this. So my u was x squared plus 1. My du was 2x dx. So this integral becomes the limit as t approaches infinity. And I'm going to go back to x's in the end. So let me explicitly say that's x equals 1 and x equals t. And this is really just 1 over u du. And the antiderivative of 1 over u is the natural log. So now I have the limit as t approaches infinity of the natural log of u from x equals 1 to x equals t. And now is the time where I'm going to go back to x's here. So I have the limit as t approaches infinity of the natural log of x squared plus 1 from 1 to t. I'm going to plug in my t and my 1, so that gives me the limit as t approaches infinity of the natural log of t squared plus 1 minus the natural log of 2. So the natural log of t squared plus 1, as t gets bigger and bigger, so does the natural log. It grows slowly, but it does go towards infinity. So this whole thing is going to go towards infinity. Subtracting the natural log of 2 doesn't do anything, so I get infinity, which is not a number, which means the integral diverges. And since the integral diverges, so does the series.